Okay, I'm going to take a quick look at 14-83. Okay. Uh, this one is a rocket of mass m fired vertically from the surface of the Earth at r equal to r1. And there's no mass, assume there's no mass lost as it travels upward, so there's no exchange of mass. Determine the work it must do against gravity to reach its distance r2. Okay, so this one is all symbolic. There's no numerical values with it. But we have a mass, me is the mass of the center of the Earth, and r is the distance between the rocket and the center of the Earth. Okay, so work is being done. Um, the work is being done against gravity for the rocket to lift off. Okay, so here's the solution for this one. So it's basically work going from position one from the Earth's surface up to some other position two, and the actual question asks how much work it must do against gravity. Okay, so because we're defining it, it's negative work because it's going against gravity, but we're just going to handle it as a magnitude in this case. Okay, since that's what the question asked for. Okay, so you can actually here's the equation for force between two objects, mass of the Earth and then mass of that object, and here would be like the distance between their centers, okay, of those two objects, or two spheres. Um, so you could actually see this equation on page 165, the central force and motion of space mechanics section. We didn't cover that section, but if you want to take a look, and this equation is actually given there. Okay, so here's our governing equation. We're going from position 1 to 2, and this is just in general, right? This is our vector form of this. Here's our vector form of the force also. So this is our generic equation, which is our work equation, and this is 14-1. Okay. Now, one of the things we need to perform an integration. So this equation is going to fall into this form, where of course this is, r, and this is r, x is r, and n is -2. Okay, so we'll go ahead and do that integration. All right. So first part of this, we're going to think about this applying the scalar form of the work equation. And it's just going to be, here's R1, R2, here's the F, that's a function of R. And all I do is substitute in for F, pull out the constants over to the left-hand side of the equation, and then do the integration. Okay, when you perform the integration, here's the end result. Okay, so gravitational constant, mass of E, the Earth, and mass of the rocket. Okay, and here's the final result. And like I said, since they define it as just the question asked for work against gravity, of course, this is going to come out to be positive because this term is going to be larger than this term, right? Okay, so that's the whole problem. Not a lot to it, just a little bit to think about um, applying this work equation. Okay, of course, you could substitute in for any numerical values and solve for it without any real issue.